Okay, good afternoon. All right, so let's start lecture. I'm going to send an email. Haven't sent it yet, so I'll send an email basically about the reminder for the final exam and some basically a few things that I recommend that you do for preparation for final exam. Okay, yeah. So I'll send it out this afternoon. Okay. But in essence, essentially, the content is from lecture 9 to lecture 24. Okay, so for this section. For the other section, they have two less lectures, so it's from 9 to lecture 22. But it's the content the same thing. Okay. So I will have the formula sheet attached to the final exam paper, so you don't have to bring it with yourself. But it's uploaded already. If you want to print it out for the preparation of final exam, that's fine. Okay. But you don't need to bring it to the final exam, so we'll attach that to the package. Okay. Yeah. The other thing is a calculator is not allowed. Okay. So you don't need a calculator basically. Okay. No other electronic device, and I recommend that you start from redoing some assignment question, tutorials, okay, lecture notes. When you still have time, then you can go over this additional exercise posted on the Connect. And I have a couple of video links that will be included in the in my email. So basically, there are some old videos from previous year, so you probably can use them as part of the reference. Okay. So anyway, I'll try to make sure me and also the other instructor will make sure we're available before the final exam. Okay, and because it's just right on our corner. If you have any questions, feel free to come to ask us. Okay, or you want a big appointment, that's fine. Okay, so online is you gotta get started now. Okay, this is what we covered from previous lecture. So we started a surface integral. Surface integral. This is the formula of surface integral, and this is actually from the formula sheet. Basically, the meaning is it gives you the net flux through a surface. Right. So it gives you the net flux, and this flux is represented basically by this vector field here. Okay. Yeah. Now we evaluate this surface integral by separating it into different cases. This is the first 1, 2, 3 cases that I covered from previous lecture. So if you have a plane parallel to xy plane, and how would you do with n hat and dA? If you have spherical surface centered around the origin, then what do we do with n hat? What do we do with a dA? If you have cylindrical surface centered around the z-axis, and what will be the n hat and what will be the dA? So basically, those are the special cases at here, in terms of evaluating surface integral. So those are part of the formula you will have, and of course, more importantly, you got to be able to interpret it when you have the formula. So what are each one of the symbols here? What's the meaning for each one symbol? So that's the most important part. Okay. So let's look at the number 4 case, which is the last case for surface integral. Okay. So this one here, I would say this is more of a general surface now. Okay. So this surface, we represent this surface using z equal to f of xy. So we have seen this quite often. This is a function, 2 variables, and this can be sketched in 3D space, which will give us a surface. Right. So that's a surface. And the more specifically, we call this is explicit surface. Okay. So why is it explicit? Because you have an expression explicitly for the z component, right? And we have done quite a few times. For example, you have a paraboloid, z equal to x squared plus y squared, and you can have a cone, right? Square root x squared plus y squared. Those are things that we have done before, right? Yeah. Now, what we want to do basically, we want to integrate the surface integral if you have a general surface described by this expression here. So basically, let's say you may have a surface z equal to f of xy. So that's more general surface instead of just a spherical, cylindrical, or just a plane. And of course, you may have basically certain type of vector fields, right, in this 3D space, and we're interested in what is this surface integral of the flux set here, right, to give us a net flux over this surface set here. So that's the idea for this case number 4. If you look at the approach that we did for case 1 to 3, the approach we did is we find the n hat. As you know, the n hat is basically the uninormal vector to the surface, right? So we typically find the n hat, and then we find the dA, right? We put them together into this surface integral, and then we evaluate. Okay. So basically, you always try to find n hat at a certain location, and also a dA at that location, right? So this piece that here, basically we can consider it's a sort of an area vector concept. So you have a small area, and the area has an orientation given by the n hat, and the area has a magnitude, which is the patch, right, dA. So that's basically magnitude, direction, magnitude concept, right? It's a vector concept. So that's the case 1 to 3. What we did, separate information, put them together. Okay. Now, for this case number 4, okay, it's a slightly different approach. So case number 4, we actually find we find this n hat dA at the same time. Okay, so we find it n hat dA in one shot. Okay, instead of a separate. You can actually do separate, but the approach that gave it to you is going to be in one shot. Actually, I'm not going to go through the approach. It's quite a bit of a lengthy proof procedures, probably a couple of pages in the lecture notes. So what I'm going to do, I'll just write down the what the results for n hat dA is. Okay, and you can take a look at the lecture notes in terms of the detailed proof. Okay, the procedures, how the n hat dA is defined. Okay, but I'll go over a little bit in terms of details in hat dA here. So it is basically the n hat dA, okay, can be found out, okay, which is this one. Okay, so this is your n hat dA at here. Okay, so it has two directions as usual, right? Whenever you have a surface, you always have one direction, two direction, so pointing either if you have a closed surface, either inwards or outwards, right? If you have a surface, maybe upward or downwards. Okay, so that is the formula for n hat dA. Now, if you look at this formula here, first of all, when you use the formula, you have to be very comfortable with each one a symbol here, right? So inside the formula, you have a partial f over partial x, partial f over partial y, negative, negative, and then 1 at here. So function f basically is given by the surface at here. Okay, so for example, if you have this is your function f of xy here, right? So then for this term, it will be negative 2x, and for this term, it will be negative 2y. Right? So that's basically how you would make use of this n hat dA formula. Okay, yeah. Now, I'm going to put this back into the surface integral. Okay, so put this back into the surface integral. Then f dot n hat dA will equal to this s. F is still the vector field dot n hat dA dot this quantity, right? So let's put this positive and negative on the outside here. So negative fx, negative fy, 1 dx dy. Okay. There we go. So that's basically the formula for surface integral when you have a general explicit surface given by z equal to f of xy. Okay. That's the formula. You don't have to actually memorize more than this one and here. I guess in the formula sheet it probably breaks down to one more step. basically assuming this vector, the vector field that here has 3 components. Okay, so M and P. So you can substitute M and P back over here, and then see what that gives to you, right? Yeah. Okay. Good. All right. So now let's examine this one here a little bit here. Okay. So then we'll examine a little more. And so looking at this surface integral at here, right? Then you look at this surface integral. The bottom line is, how do we evaluate this one here? So once you substitute n hat dA at here, now you see the evaluation of the surface integral essentially boils down to this variable x and y now, right? So it's just like the other cases of surface integral. So it's a 3D surface, okay, in 3D space. But when you evaluate surface integral, as you can see, you essentially concentrate only on 2 variables instead of 3 variables, right? So here you have x, y. Here you have a d phi d theta. So that's right, 2 out of the 3 of those spherical. And cylindrical, you have a dz d theta. So that's also 2 out of 3 for the cylindrical. Okay. And then in this case that here, with this formula, so you end up with just x and y, so the z is not in the picture anymore, right? So basically, you will have to focus on x and y, but if you imagine this m is a function of x, y, z, n could be a function of x, y, z, and p could also be a function of x, y, z, right? Okay. So what do we do with the z then? We can't leave the z here because there's no z, right? It's an integral with respect to x and y. So for this formula, right? For this formula here, what do you do with the z? You're going to replace the z with exactly. You're going to replace the z with f of x, y. Okay. So that's a very crucial steps here. Okay, so whatever the surface is given at here, so your z has to be replaced with this f of x, y at here. So that's the part you have to remember, huh? Because the formula sheet at here doesn't, for example, the formula is probably just up to here. So the formula cannot specifically tell you all the details, but you have to remember the z is replaced by this, right? Okay. Okay. So once you know the z is, then you're dealing with just the x and y now, right? It's going to be x and y. The question basically, the next question basically is, how do I find the limits for x? How do I find the limits for the y? So that's how you can evaluate this integral, which is double integral basically. Okay? Yeah. So how do I find the x, y then? The x, y is actually quite easy. You find your x, y based on the shadow, okay? Based on the shadow of your surface in x, y plane. So let's say if this is the shadow at here. Okay, let's call it shadow R. Okay, and the x, y limits are determined by the shadow of the surface or the projection of the surface in the x, y plane. Okay, so that's another thing. The formula probably won't tell you, but you have to x and y limits, okay, are determined by the shadow of the surface, right, in xy plane. So that's how you can determine the xy limits at here. Okay, so I guess I need to. This is a couple of important things that you need to basically remember. First of all, you need to replace the z with f of xy, so no z anymore. And second of all, then you remember finding the xy limits are purely based on the shadow of the surface in the xy plane. Okay, yeah. So those are 2 crucial points. If you can remember this, the rest of the work is basically just a double integral as you did in the previous lectures, exercises. Yeah. So it's like this. Let me redraw this one here. Basically, for example, if you have a surface, right? If you have a surface here, and you project the surface, okay, into the xy plane. Okay. So you project that over here. Okay. Yeah. So this is your z equal to f of xy. So now you're integrating over this surface S. So your integration is over the surface S. Okay? Yeah. Just like you're doing integration over a region R in a planar XY plane, or you're doing integration over a solid region D. Now, I keep emphasizing this: when you're given a question to integrate over certain things. So bottom line is, what are we doing? We're basically trying to sweep through the whole region, right, or the whole solid region, the planar region, without any redundancy, or just recreating what's given, right, the region at here. Okay, yeah. So if I look at this one here, if you're going to scan through this surface S at here, scan through it, or recreating this surface S, how do we do that, right? So here is one approach to do it. Here's a shadow, so we can, let's say I pick a dx, dy as the order. Then we can draw arrow lines, okay, in the x-axis direction. Okay, so when you draw this arrow line here, you have first context, second context. Let's give you x min, x max. Okay, so here you have a x min, and here you have x max. Okay, so as you're going from x min to x max, then basically what happens on the top is you create essentially the green curve, right? The green curve there. Okay, so scanning from here to here, creating this curve segment on the surface. Okay, and the second step, you move this arrow line from one end to the other end, finding y min and y max. Okay, so moving from this arrow line from here to here, essentially you're sweeping from one end to the other end. So then you can imagine the green curve segment, what it does is basically start to scan through, right? Scanning through this top surface from one end to the other end. Okay, so that's how you can recreating or scanning through this given surface, or integrating through this given surface at here. Okay, so that's the idea, finding the x min, x max. It's the same idea for double integrals or triple integrals here, right? How you can go through this surface here. Okay, so we'll look at an example shortly, just evaluation of this surface integral. Okay. Okay, but before we move on here, I want to take a second look at this surface integral formula. Okay, just to look a little bit in depth into this formula here. So I'm gonna maybe just rewrite this as okay. Just rewrite this one here. Okay. Okay. Again, I'll draw the some sort of surface at here. So I didn't give you the detailed proof as to basically this n hat dA. As I said, it's negative fx, negative fy, and 1, and dA, right? Positive, negative. Okay. Yeah. So I didn't give you the detailed proof at here, but you can find the proof in the lecture notes. That's fine. Okay. But let me give you a little bit more intuitive. Actually, it's not a proof. It's some prior knowledge that we learned in here. Let's see, huh? Yeah. First of all, okay, let's look at the d n hat here a little bit. Okay. Now, as I mentioned, what is n hat here? N hat is what? It's a unit normal vector to surface S, right? To this surface S at here. Okay, this is your surface S at here. So that's the physical meaning. n hat is a unit normal vector to the surface S, right? Okay. So forget about this surface integral for temporarily. Okay. Let's say if I ask you a question now. I give you a surface at here. Can you give me n hats, right? So basically, given z equal to f of x, y, what will be a n hat, okay, for this surface at here, using prior knowledge that we learned? Okay. What kind of vector? First of all, maybe instead of n hat, the first question let's ask is, can you give me a vector that is perpendicular to this surface at here? What vector is perpendicular to this surface? Greetings, right? The greetings. The greeting vector is perpendicular, but is this greetings? No, that's this one. This is something when a student asked me in the office too, and I think I feel this confusion often among the students. There are two greetings, right? When you're giving a surface, there are two greetings. Okay, one greeting is what? Del f, right? But this greeting, what dimension is this greeting? No, this one here, 2 dimension, right? This is 2 dimension. This one gives you fx, fy. Okay, but there's another greeting, which is a greeting vector perpendicular to this surface at here. And what's that greeting? That greeting, how you find that greeting? Basically, it's a greeting vector at here. I won't write it here. I won't write it in yet. Let's call this n vector here, right? And that greeting is coming from what? Greeting to the surface coming from. Okay, so you basically let w equal to z minus f of x, y. Okay, so you create a new function, right? Create a new function, w equal to z minus f of x, y. Okay. If w equal to 0, then you get back to this given surface, right? Okay. Yeah. So now, if you remember, so this is a function of 3 variables, isn't it? Right? This is a function of 3 variables. So w equal to 0, if you recall, what do we call that? It's called a level surface, right? So it's one level surface. So you can calculate del w. That's the second grading I'm talking about here. Not the del f, it's a del w. So del w is the 3D vector here. So this one here, wx, wy, wz, partial w for partial x, partial w partial y, and partial w partial z. Okay, so that's the 3D vector here. And this one is perpendicular to the surface, w equal to 0. Okay, so this one is perpendicular to this w to 0 here, or the z equal to fxy. Okay. Maybe this is a good time here. What does the del f perpendicular to? Level curves, right? Yeah. So make sure that the difference that is here to be a very clear concept, right? Clear concept what you're dealing with. So this one is perpendicular to the surface. So let's calculate, right? So this is your w, z minus f of x, y here. If I calculate partial w over partial x, so the first quantity, it has no z component, 0. Second quantity has a function of x, y. So this gives you negative fx here. Partial w, partial y give you negative partial f or partial y. Last one, partial w, partial z give you what? 1. So see, that's your del w, right? And this is a greeting vector to the surface, which is perpendicular to the surface. But what I need is a unit normal vector, right? So what do? Normalize it. So we can normalize this to get a unit normal vector. So if I normalize it, what do we get? We get basically negative fx, negative fy, and 1 divided by its length. So fx squared, fy squared plus 1. So that's your n hat. Okay, that is your n hat at here. So if you look at this surface integral that we're talking about here, this is your surface integral, okay, for this particular type of surface. And n hat, we're actually able to derive based on our prior knowledge, which is this one. Okay, that's your n hat. Is that good? Yeah. But what I give it to you, but we don't need the n hat, right? We're really needing this formula is what? It's the n hat dA. So n hat dA, I didn't derive, but I wrote it down already, right? So this is your n hat dA at here. Okay, it's your n hat dA. So if I got the n hat, and I can derive for the dA, isn't it, right? So I can derive the dA, and dA can be derived, which is this quantity. Basically, it's fx squared plus fy squared plus y, and dx dy. So that's your dA. If you multiply the n hat dA together, you get the formula n hat dA. Okay? Yeah. Now, why am I taking this extra step here? Really, you actually don't really need this extra step in terms of this surface integral calculation. The reason is it's not required; it's optional. The reason is actually this is also a very important formula, dA. Okay, this is also a very important formula. I'm not going to test you, but for example, there's a very typical question. You have a certain maybe shape or geometry covered by a surface. Then maybe the customer will ask you, can you give me the surface area of this geometry, right? Okay. So how do I mathematically calculate this surface area? How do? You take a dA, then you integrate the whole dA. You basically, here you get the surface area, right? This is your general surface area formula, isn't it, right? So all you need to do is replace the dA with the formula at here. There, that's another formula, right, derived from this part of the lecture here. So you have a surface area formula for a general surface given by z equal to fxy. Okay. So this is optional. You don't have to. This is not actually in the lecture in the formula sheet, but I feel like you probably it's good to know. Okay. Yeah. So that's sort of a detailed breakdown into n hat and dA. Okay. Now second comment. Okay. Second comment is, so let me write down the n hat dA again. Okay. Which is positive and negative fx fy 1. Okay. So and dx dy. Okay. So this is your n hat dA, right? Okay. Now there's a positive, there's a negative here. So which one shall we use, right? Now what's the meaning of this positive and negative sign for inside this formula? And when do we choose positive and when do we choose negative? Huh? Yeah. Okay. So positive or negative, you know, you have to think in terms of the direction of the vector. Huh? So let's say I'll just somehow draw a surface at here. Okay. So if I have a surface at this location, so you could have n hat dA this direction, and you could have n hat dA this direction, right? So there are two directions, okay, perpendicular to that surface. So maybe I'll let you take a guess at here, educated guess. So for the red one, should I be corresponding to the positive or negative sign? The positive, right? So this is the positive here. Of course, this is negative. Okay, yeah. So this one here, so why is it this one corresponding to the positive, this one corresponding to negative here? So basically it's a positive, and then you have negative this, and the 1, right? It's a negative, it's a negative, okay? Yeah. You can think of it in terms of, let's say, I don't really care what the first two components are. When you have a vector, that the last component is 1. Okay, so when you have a vector, the last component is 1. And you can imagine, if you draw the vector out in 3D space, that arrow must be always somehow pointing what? Upward, right? So there should be always some kind of a positive z component, okay, because of this 1 at here. So that's why this is positive. We sometimes in a question you probably see upward flux. Okay, so you have a surface and asking for upward flux, and that word basically means you pick the positive sign at here for this formula. If you have a downward flux, then you pick this negative sign. Okay, so that's how you can determine what sign to pick for this formula right here. Is that clear? Yeah. Okay, good. So this is all about the details of this simple formula here, right? So let's take a look at a couple examples. Okay. Given a vector field, it's a very simple field. So F equal to Z k hat. Also a surface. It's a paraboloid. The Z is between 0 and 1. So here is a paraboloid. If you draw it out, this is 1, this is 0. So that's your surface at here. Okay. And you can sketch the F, which is very simple F, but you don't have to. Okay. In this case, we want to calculate this F dot n hat dA. So the net flux through this upward flux. Okay, so we want to calculate the upward direction flux. Is that good? Okay. Okay. So before I do any calculation in here, yeah, and I want you to think of, if you can interpret this correctly, you answer this question correctly. What would you think the answer for this calculation is? Would that be a positive, or negative, or 0, or whatever, right? What do you think the calculation of this surface integral or the net flux would be? Would that be a positive number? Would that be a negative number? Or any other type of numbers? Yes? No, just the bottom here. There's no top cap. Yeah, it's positive, right? Yeah. How do you get a positive? You have a, I guess, because we want it upward flux, so you can somehow draw the upward flux, right? So this is your n hat. It's always pointing upwards, right? Yeah. And second of all, okay, you can imagine or visualize the vector field out, because it's a Z k hat. So the vector field somehow is always, okay, pointing upwards, okay, like this. So there's, as it go away from the xy plane, and you have a bigger magnitude. Okay. So now you can look at this green and the red. So you're looking at F dot n hat. So apparently there's always a positive number, right? So overall the net flux, and the upward net flux, will be a positive number. So this will be positive than 0. Okay. So that's a quick actually check. Sometimes, you know, if your calculation is not in line with your educated guess, then you can always go back and check what is going on here, right? Yeah. So let's do the calculation in here. Okay, let's do the calculation, and we write down the n hat dA first. Okay. Upward flux basically means, okay, we take the positive sign. Okay. Yeah. So that's negative fx, negative fy, and 1. And you look at the surface area here, your f of xy is equal to x squared plus y squared. So, oops. Okay. So your n hat dA, okay, is equal to negative 2x, negative 2y, and then 1 dx dy. Okay. Now finally we're going to replace, right, we have the f here, which is 0, 0, z dot negative 2x, negative 2, negative 2y, 1, and then dx dy. Okay. Okay, and calculate this dot product. We get just a z dx dy. Okay, s. So now what do we do with the s? What do we do with the z? The z is going to be replaced with x squared plus y squared dx dy. Okay, that's good. So now everything is in terms of x and y, and the determination of the xy limits, if you recall, is purely based on the shadow of this surface in the xy plane. So this is a surface that is here, and the shadow in the xy plane is this guy, which is a circle, right? So the shadow right here is x squared plus y squared equal to 1, because the top one is z equal to 1. Okay? So the shadow is in the xy plane is a circle. So this essentially, at this stage right here, you can replace the s using the r now, right? It's using the shadow here. Okay? This is becoming a very typical double integral question now. So if you think of the double integral, we only have two different approaches for evaluating a double integral. One is Cartesian, and the other is what type? Polar, right? And you use the polar when you have a circle centered around the origin, or slightly off the origin. So you can actually, from here, instead of using Cartesian, you can use polar now. So using polar, basically replacing the x with r cosine theta, replace the y with r sine theta, and then our dx dy become, that's right, yeah. So limits for r and theta are based on the shadow. So this is just a circle, so r is 0 to 1, theta goes 0 to 2 pi, so that's 0. So that's it. Okay, it's a very simple integral. You get pi over 2, okay, which is a positive number, right? Yeah. So that conforms with our projection. Okay. Okay. So this is the type of evaluation for this kind of integral right here, huh? Yeah. So let's take a look at one more example, then we can move on, huh? Given a vector field and a surface which is part of the plane in the first quadrant, okay, and we want to calculate this surface integral. Okay, surface integral here. You can always sketch so here's x plus y plus z equal to 1. Okay. Basically, this triangle here is the S. That's the first quadrant, right? Yeah. Okay, so it's a very typical surface integral, right, for the case number 4. Yeah. Of course, you have to. This S is given in x plus y plus z equal to 1. Okay. So what do you do first? You need to write this x plus y plus z equal to 1 into the format exactly like the case number 4, right? Yeah. So case number 4 asks for z equal to f of x, y. So what do I do with this expression here? We write it in the format of f of x, y. Okay, so write it in this format here. And now we can go ahead and calculate this n hat dA. So let's say I'm still want upward, Let's see, upward flux. Okay, still upward flux. N hat dA, negative fx, negative fy, and 1 dx dy. Okay, I want you to calculate. Okay, I want you to calculate this one here. So this is your fx right here. This I want you to see if you make a mistake or not. So you do this calculation. Here's your fxy. Calculate these two partial derivatives. Okay. What do you get? Did you get a 1, 1, 1? Yeah. The reason I'm asking to do this is, if I remember correctly, probably test this question sometime in the final exam before. A lot of people put a negative here. So, guess what the danger is? This is always the first step, right? You put a negative sign wrong, the rest of the calculation will all wrong. So you have to be very careful with the negative signs, okay? And in particular, sometimes if you choose the other direction, you have another negative. So there's so many negatives, during exam setting, it's just too overwhelming. So 1, 1, 1 for this one here, okay? Now then we can calculate this surface integral. Your f vector field is x squared 0 3y squared dot this 1 1 1 dx dy. So that gives us x squared plus 3y squared and dx dy. Okay. All right. So now everything is in terms of x and y. So you can go ahead, try to find x and y limits. So x, y limits are based on the shadow. So you look at this question here. Your shadow is this triangle over here, right? And you can use the typical approach. This one here, I think a Cartesian will work. So you draw, let's say dx first. You draw the arrow line in the x direction. First contact give you x mean. Second contact give you x max. So second contact is on this edge here, because you have the plane over here. So this edge is when z equal to 0. So this is basically x plus y equal to 1, right? So your x max will be y minus y. Okay, so that's your x max. And then you sweep this arrow line from one end to the other end, to the other edge, to find the y mean, y max, and that's 0 to 1. Okay, so you can calculate this double integral as euro, so you get 1/3. Okay, so that's the should be fairly straightforward. Okay, any questions on this case number 4 surface integral? Okay. In the lecture notes, I have included 2 more cases, case 5, case 6. Okay. For your interest, you can take a look at the other 2 cases. Okay. So they are optional. They are not going to be tested in final exam. So basically, the case 5 will be on implicit surface, and case 6 is on describing when a surface is described using a parametric equation. Okay. So those are the 2 additional cases you can look at it. So now you can imagine if you have ever seen a surface integral question, then the first logic step for you to do is you actually had to make a decision which case you wanted to use to evaluate this surface integral, right? Yeah. So make a educated guess. Okay, so here is a spherical surface. Okay, so I might use a spherical formula, right? Yeah. If you have a surface which looks like this, so you use the case number 4. So that's how you can make a decision. How would you evaluate this surface integral? Okay, so there's only 4 different options. So now that brings us back to the last topic of this class now. Okay, so last topic we're going to have 2 very important theorem. One is called Divergence theorem, and the other is called Stokes theorem. Okay. So this is basically what we're going to cover for the rest of the today and last lecture. Okay, and if we got a little bit of time, next lecture I can do a little bit review, an overall review there. Okay, so before we jump into this divergence theorem and Stokes theorem, as you probably see, you see a new term at here, divergence, right? So that's not the movie. It's the actually what's so let's look at this term in here, divergence. What is this guy? What does divergence mean? Okay, and what's the definition of that? And how do we interpret this divergence here? Okay, so this is the first one. So more precisely, okay, I should say divergence of a vector field at a point. Okay, at a point. I'll write down the definition first, and then we can discuss the meaning of this one here. Okay, yeah. Definition of divergence is this. It's limit. Okay, so basically, let me write it down first. So here we have an expression, limit expression in here. Okay, it's a definition. So let's look at this this guy here. What does it mean first for? Yeah. So if you look at forget the limits first. First we'll look at this fraction. Right. Look at this fraction. So this fraction, the numerator is a surface integral. Right. It's a surface integral. And what's this surface integral? There's a little bit difference, huh? I have a circle at here, isn't it, right? A circle. So basically, what this means is what? That surface is a closed surface. Okay? Yeah. Just like our vector line integral, it's usually just the integral, right? But sometimes we have a circle there. So basically means it's a closed curve. Okay? But in this case, it's a closed surface. Yeah. The surface? The surface, there's no clockwise or counterclockwise, right? It's closed. But it does, as I'm going to actually mention, it does have orientation, right? There's outwards, there's inwards, okay? Yeah. So this symbol here basically means you're calculating the surface integral or the net flux through this surface S, which is a closed one, okay? Inside this vector field F at here. So that's basically what this means here. Is that okay? Right? The delta V at here. Okay? So delta V is the volume enclosed by the S. Okay, that's the relationship. So you have a surface S enclosed. Then how much volume is enclosed by this surface S? Indicate that with the delta V. Okay, yeah. So now you look at the fraction here. The top one, physical meaning, right? What's the physical meaning of this surface integral? You give us what? Huh? So not a surface area. Surface integral give us the net flux, right? Give the net flux through this enclosed surface. Okay? So you have a net flux through this surface S, and divided by the volume that it's enclosed by this surface S. So it's like what? If you recall that the way we define the circulation density, you have a circulation divided by what? By the area, right? That's circulation density. So now you have a net flux divided by its volume. So this one here, so technically speaking, we get what do we get? So it's still a density concept, right? So what kind of density concept now? Flux density, right? So you get a flux density here. And now we let the delta V go to 0. So when delta V go to 0, basically we're talking about what now? We're talking about a single point. So this guy here basically give us a point flux density concept. Right? Point flux density concept. And we denote this term, okay, using a new symbol called del dot F or DIVF. Okay, so we denote this term. It's actually it's not really denoting it. It's actually derived. It will be this one here. Okay, so you have the right side here, which is a definition. Okay. It's a definition for a point flux density concept, and that is defined as this del dot F. It can be proved actually. Okay, in the lecture notes, I did give you the proof. There are 3 pages proof of there. So you can prove these limits at here is the del dot F, and I'll write down the expression for the del dot F. Okay, yeah. So this is basically the third operator that we're learning in this class. What's the first operator we learned? Not partial derivative? Yeah, okay, let's consider the first because we're going from straight D to partial, right? Okay, so then what's the second one? Gradient. What's the third one? Curl. The fourth one is this guy here, the divergence. Okay? So I'll explain a little bit more from the divergence here. So now you have a partial to del cross, and now to del dot, right? To del dot. Okay? Yeah. Not really from this to this to this, but these 3 here more or less are parallel to each other. Huh? Yeah. So the del dot F, okay, is called divergence of a vector field. Okay. At a point. Okay. And what this expression for this one here, using the limit, you can prove that this expression. So I'm not going to prove this one here now, so I'll just write it down this one here. Okay, so it's partial m partial x plus partial n over partial y. Well, maybe I'll write down one more step here. Just so del is partial this, right? So del is a vector. Dot this vector function f, which is m and p, okay, in general. So dot product, when you calculate dot product, you calculate the product of each component and you add them together, right? So you get partial m over partial x plus partial n partial y partial p partial z. So this is your calculation of divergence. Okay, so divergence of a vector field at a point, just like the curl of a vector field at a point, or gradient of a vector field at a point, right? Okay, so here's your formula for divergence at here. Okay, here's the formula of divergence. So if you look at the formula of divergence, it's very easy to calculate. First of all, it's a scalar. Okay, it's different. It's different from the curl. Curl is a vector, but divergence of vector field gives you a scalar quantity, right? Gives scalar. That has to be very clear. And the gradient of a vector, a gradient of a scalar function, give you a vector, right? So each one of the results here. So let's come back to the divergence study here. So what exactly is the divergence of vector field? How do we interpret this divergence of a vector field then, right? Okay. So now you look at the divergence. If I write it, okay, using very simple language or using the Lie language here, it's basically a net flux, right? So that's your numerator, right? The numerator gives you the net flux, and denominator is what? It's a volume concept. So divided by, let's say, unit volume. Okay, so your divergence is basically it's a net flux divided by the unit volume at here. Okay, the unit volume. So you can understand this kind of question as, okay, so the divergence, okay, it gives a amount of a flux, okay, entering or leaving a point. Okay, so basically it gives you amount of flux entering or leaving a point. What does that mean? So you calculate divergence, you get the flux density at the point. So you probably get a positive number, for example, right? Or you probably get a negative number. Okay? So what does positive mean? Meaning there's more entering. No, the other way around. No, when you have a positive, right? When you have a positive divergence, it actually means there are things coming out of the point, right? Basically, if you have a positive, okay, divergence, okay. If you have positive divergence, meaning you have a flux coming out of the point, okay, and so that point you consider as what? As a source, okay, as a source. So if you have a negative, you basically consider it as a sink, okay, as a sink. I have a few very daisy pictures. If you want to see, I can show you later. Okay, basically showing the source and the sink. Okay, very simple illustration. If you turn on the tap, what do you see? You see water keeps coming out of here, right? That's basically it's a positive divergence. There's a source here. And if you go to the courtyard, the water all goes into that hole, so that's a sink, basically. Okay, yeah. So that divergence calculation give you an idea. Right, here's a vector field. Okay, give you an idea at that single point. Is the flux going into it or coming out of it? Right? Is it a net source or is it a sink? So let me give you a simple calculation and another illustration in here. Okay. So let's say I have v equal to 2x minus y squared, 3z plus x squared, 4y minus z squared. Yeah. Right. So let's say this is your vector field. Okay. This is your vector field here. Then we calculate the divergence of this vector field. The calculation using the formula that I showed you at here, partial m partial x plus partial m partial y plus partial p partial z. Here's your m, here's your n, here's your p. Okay, so it's very easy calculation. So you should get what are we going to get? So partial m over partial x, we should get what? 2, right? Partial n partial y, there's no y, so 0. Partial p partial z, negative 2z. Okay. What's going on here? Plus, plus. It's not a vector, it's a scalar, right? Okay. So that's your divergence. Now let's pick a specific point, right? Let's pick 1, 2, 3. Okay. In the 3D space, let's pick 1, 2, 3 location. So at this location, what is this value of the divergence at here? So what do? We replace the z with 3, right? Replace the z with 3, so we get negative 4. Okay, negative 4 here. Okay, so that's your divergence of this vector field at that location, which is a negative number. So basically means that location will function as a source of sink, right? So you can sometimes you can actually take a quick decision or judgment here. Let's say if I have a small volume at here, which is placed inside a vector field like this. Okay, place the vector field like this, or maybe placed in a vector field like this. Okay, or maybe placed in the vector fields like that. Okay, yeah. So here's your V and V and V like this. Okay. So now I want you to take a guess now. What do you think within this area, within this small area here, what do you think the sign for the divergence, okay, for each one of the case here, each one of the cases? For the first one, del dot v, what could be possible the value for this? The second one, del dot v. The third one, del dot v. Let's deal with this easy one. What do you think of this third case here? Del dot v. What do you think it's positive, right? Good. And third one here, what do you think? Yes. What about this one? Good. Right? Yeah. So now you get idea what really del dot v is telling you, right? Yeah. Okay. Very good. Now, there's a few expression at here, a really interesting expression. I'll write it down here, but you may not be able to actually accept it right away. So, but they're interesting things to know though. Okay. So there's first expression is this del. If you calculate this expression, del cross del f. Okay, if you calculate this one, del cross del f. Actually, this one I think it should be quick to know. What does del f give you? First of all, plain idea. What does del f give you? Grading to vector, right? I mean, it's a scalar function. You calculate the gradients. So technically, what does it give you? It gives you vector fields, isn't it, right? Now, in the previous lecture we learned, del f actually gives you a very special field. What do we call it? Conservative. And how do you check the conservativity of a vector field? You calculate what? Del cross. So then this one is supposed to give you 0. Okay? So del cross del f will be 0. Okay, so now you see you're putting things together, right? It's actually there's an interesting thing here. It's called you can use a very simple language. Gradient can't curl. Okay, gradient can't curl. And I actually bumped into a very funny cartoons last night. Not sure if you can. This is the next one I can see the Gradient can curl. So this is a gradient here. It's asking who's on my team. What's this plane? I don't know if you get it. His plane curling, so nobody wants to be with him, right? So because why? Why? Because gradient can curl, right? So that's basically what it means. Okay. First time showing this picture. And second one here, you can calculate if you're given a vector field, right? Give you a vector field, okay, and you calculate the curl, right? This is calculating the curl, and then you calculate the divergence of the resulted vector field. You can show that this is 0. Okay. Now this one here actually has something to do with the divergence theorem that we're going to cover after this one. Okay. So similarly, okay, I'm not going to explain this for now, but you can actually use a similar language. So the curl whose divergence will be 0, any curl, right? So what can you see? So the curls, what? Can diverge. Okay. So when you have a calculated vector field, which is the curl of a certain vector field, and then if you imagine, right, if you wanted to calculate the divergence for the vector field at a certain point, you will always get a 0. Okay, the divergence is always 0. And we can explain that actually once we learn the divergence theorem. Okay. As a matter of fact, when you have if a vector field's divergence 0, there is a special term here. So this is called a solenoidal. So we don't have to know this. So this is basically a solenoidal field here. Okay. Honestly, I'm not sure what that means actually. So those are two things. Okay. It's a sort of a combining all this thing of combining the different operators together, right? And there's a physical meaning actually behind the two expressions added here. Good? All right. So now I think we're ready to talk about divergence theorem. It is also called Gaussian theorem. Okay, so it's a divergence theorem. It's basically, it's actually, as we're going to learn here, it's actually a 3D, the 3D analog of the Green theorem. Okay, so we learned the Green theorem, right? So this is actually 3D. I'll relate that to the 2D, to the Green theorem after we finish this one here. Okay, so divergence theorem. First, let's write down the definition or the theory of this one here. Okay. If surface S is a closed surface, so now the keywords that are here, right? The first keywords, it's a closed. It's not a open surface that are here. Okay. It's a closed surface. Whenever you have a closed surface, then the surface will be bounding a region D, right? So there will be a solid region D bounded by this closed surface. Moreover to this, okay, and then we see that with normal pointing outward, okay, pointing outwards. So this is the condition for the precondition here for the divergence theorem. It deals with a closed surface, and the normal for the surface has to be picked as the outward direction. Okay, so that's the this sentence here. So if this is the surface here, and given a vector field F equal to M N P. Okay. So the MNP is defined and differentiable more precisely, okay, over region D. Okay. So basically you pick any point within that region D enclosed by the surface S, then the f is always defined and it's also differentiable. So after you take a derivative, you plug in the point and you still get a defined point. Okay, so it's not anything like a jump, right? Yeah. Good. So that's the conditions listed for the divergence theorem. Then the calculation here is basically you have an expression in here. So I'll write it down first. Here's a surface integral. Okay, that's it. That's your divergence theorem formula. Okay. So that's your divergence theorem. Okay, so let's look at this formula here, huh? Yeah. So this formula is actually quite simple. You look at the first of all, look at the left side here. It's a surface integral, right? So that's basically surface integral over this enclosed surface S. So technically speaking, what does the left side give us? Remember, when we integrate this surface integral here, the condition says it has to be the normal pointing outwards, right? The normal pointing outwards. So for this particular one here, this is essentially referring to outward flux. Okay, so this is basically the outward flux set here. Okay. And then this side here, right? This side here is a triple integral. It integrates through this region D enclosed by the surface S. And what does it integrate? It integrates the divergence of the vector fields. Remember what I just said? What does divergence of vector field, what's the physical meaning of it again? It refers to what? The what? The flux density, right? So it basically it's like this. So you have a surface S and here's a D. We integrate within the D here, we integrate the flux density within the D through this whole region D. So integrate the whole flux density around the region D, and what do we get? We get a total outward flux. So this is basically the meaning in it here, right? So the left side here is divergence integral or integral of flux density. Okay. So integrating flux density over a solid region D enclosed by the S give you the total flux out of this surface S, right? It's pretty natural interpretation, right? So it's like you integrated mass density and you get the total mass. Yes.
dA vector is m hat dA, right?
Here?
Yeah.
Yeah, in hat dA, that's right. Yeah. So this is basically in hat dA. Yeah. Very good. So divergence theorem basically connects the triple integral, okay, with a double integral. Okay. So you have a double integral here, a triple integral here, and that's basically what it connects it here. Okay. Yeah. So now you can imagine, huh? Let's say I'll give you an example here. So we're not doing anything in here, just give you an example. Let's say, for example, I have I have a surface, but you have S1 and S2. Okay, so you have a region which is enclosed by S1 plus S2. Okay, so that's possible, right? Okay, yeah. Then, if you're going to calculate, so S equal to S1 plus S2, if you're going to evaluate this surface integral at here, so if you're only looking at the right side, then what you're going to have to do is you're going to have to do a piecewise, basically, integration, right? S1 and S2, and add them together. Okay? Yeah. Or alternatively, if you don't want to do this, now you have an option now, right? So the option is to do what? Is to do this. Okay? So you can also calculate this triple integral. Okay? So it really depends on the situation at here. Sometimes you do this side, sometimes you do this side. Okay? Maybe one side is actually will be much easier. So I'll give you an example. You'll see the reason I'm saying here. Okay. So we'll get a very quick example here. So F equal to zk hat, and S is x squared plus y squared plus z squared equal to a squared. So it's a sphere. So then what is the net flux, okay, out of this spherical surface at here? Okay. As I said, you can calculate the surface integral as Euro, but maybe I will try this divergence theorem for this question. So we need to calculate del dot F. Here's your F at here. So calculating the del dot F is actually basically 0 plus 0 plus 1. So partial m, partial x, partial n, partial y, and then partial p, partial z. So that's just a 1 here. So this thing here is just equal to 1 here. Right? Just equal to 1 this. And now you look at this one here. This essentially refers to what? Refer to the volume of this sphere. And the volume of the sphere is basically 3 over 4 pi times a cubed. So that seems to be a less computation than carry out the surface integral, right? Okay. So we'll look at a couple more examples, and then we'll look at the last theory, Stokes theorem, in the next lecture. Okay? Yeah.